Assalamu alaikum. Today we want to talk about chapter 13 part 2, properties of solution, and we want to start with this figure 1322, phase diagrams for a pure solvent and for a solution of a non-volatile solute. Now, how will the phase diagram of a solution and hence its boiling and freezing point differ from those of the pure solvent? Now, if we look at this phase diagram, the vapor pressure curve of the solution in a blue line will be shifted downward relative to the vapor pressure curve of the pure liquid. Black line, at any given temperature, the vapor pressure of the solution is lower than that of the pure liquid. Recall that the normal boiling point of a liquid is the temperature at which its vapor pressure equals 1 atmosphere. So, at the normal boiling point of the pure liquid, the vapor pressure of the solution will be less than 1 atmosphere. Now, therefore, a higher temperature is required to attain a vapor pressure of 1 atmosphere. Thus, the boiling point of the solution, shown here, is higher than that of the pure liquid, as you can see here. Now, the increase in boiling point relative to that of the pure solvent, delta Tb, is a positive quantity, and we will talk about it later. Now, the same is true for the freezing point here. For a pure solvent, this is the freezing point, whereas for a solution, it is lower. So we can say that the freezing point of the solution is lower than that of the pure solvent. So non-volatile solute-solvent interactions also cause solutions to have higher boiling points and lower freezing points than the pure solvents. Now here you can see this is called the triple point of solution, triple point of solvent. These are the three states: solid, liquid, and gas. This is the boiling point of solvent. This is boiling point of solution. This is freezing point of solution, and this is freezing point of solvent. So the change in boiling point is proportional to the molality of the solution. So delta Tb equal Kb times molality, where Kb is called the molar boiling point elevation constant, depends only on the solvent. And here we have some typical values for several common solvents. For example, for water, Kb is 0.51 degrees centigrade per molal. Therefore, a 1 molar aqueous solution of sucrose will boil 0.51 degree centigrade higher than pure water. But if you have, for example, an electrolyte solution, if you have like NaCl, for example, if you have 1 molar aqueous solution of NaCl, which means it is 1 molar in Na plus and 1 molar in Cl minus, making it 2 molar in total solute particles. So as a result, the boiling point elevation of a 1 molar aqueous solution of NaCl is approximately 2 molar times 0.51 degrees centigrade per molar, and this is equal 1 degree centigrade, twice as large as a 1 molar solution of a non-electrolyte such as sucrose. So it is important to know whether the solute is an electrolyte or a non-electrolyte. The change in freezing point can be also found in a similar way. Delta Tf equal Kf times molality. Now, the values of Kf are also found on the same table, and delta Tf is directly proportional to the molality. For example, Kf for water is equal 1.86 degrees centigrade per molar. Therefore, one aqueous solution of sucrose or any other aqueous solution that is 1 molar in non-volatile solute particles such as 0.5 molar NaCl will freeze 1.86 degrees centigrade lower than pure water. So The freezing point lowering caused by solutes explains the use of antifreeze in cars and the use of calcium chloride CaCl2 to melt ice on roads during winter. So again, here we have the two formulas, one for boiling point elevation and one for freezing point depression. Note that in both equations, delta T does not depend on what the solute is, but only on how many particles are dissolved. Now let's look at this sample exercise, calculation of boiling point elevation and freezing point depression. Suppose we have this automative antifreeze consists of ethylene glycol, a non-volatile electrolyte. Calculate the boiling point and freezing point of 25% mass percent solution of ethylene glycol in water. So we are given contain kada, so the plan is to calculate the boiling point. We must express the concentration and molality. Let's assume for convenience that we have 1000 grams of solution. Because the solution is 25 mass percent ethylene glycol, the masses of ethylene glycol and water in the solution are 250 and 750 grams respectively. So ethylene glycol 250 and water 750. Using these quantities, we can calculate the molality of the solution, which we use with the molar boiling point elevation and freezing point depression freezing constants, as I showed you, to calculate both delta TB and delta TF. Then we add delta TB to the boiling point and subtract delta F from the freezing point of the solvent to obtain the boiling point and freezing point of the solution. So let's calculate the molality. Moles of ethylene glycol divided by kilogram of solvent. Then you divide by the molar mass of ethylene glycol, and then you can convert also to kilogram, because the law says molality equal moles of solid per kilogram of solvent, and you have this number 5.37 molar. Now we can use the equations we showed you before to calculate delta TB, and these constants will be given, and you get these values. Then after that, the boiling point and freezing point of the solution are then boiling point equal normal boiling point of solvent 100 degrees centigrade plus delta TB, which is 2.7. So it is 102.7 degrees centigrade. Freezing point equal normal freezing point of solvent 0 minus delta TF 10, and you have minus 10 degrees centigrade. So these are the values that we obtain. Then you can solve this practice exercise, which is similar to the sample exercise. After that, we want to see this sample exercise, freezing point depression in aqueous solutions. Now suppose you are asked to list the following aqueous solution in order of their expected freezing point: 0.050 mol CaCl2, 0.15 mol NaCl, 0.15 mol HCl, 0.050 mol CH3COH, 0.10 mol sucrose. Now, analyze. We must order 5 aqueous solutions according to expected freezing points based on molalities and the solute formulas. Now, the lowest freezing point will correspond to the solution with the greatest concentration of solute particles. Now, to determine the total concentration of solute particles in each case, we must determine whether the substance is non-electrolyte or an electrolyte, and consider the number of ions formed when an electron ionizes. Solve. CaCl2 and NaCl are strong electrolytes, so they ionize completely, whereas acetic acid is a weak electrolyte and sucrose is a non-electrolyte. So the molality of each solution in total particle is as follows. 0.05 mol CaCl2 equals 0.05 mol in Ca plus 2 and 0.1 mol in Cl minus. So we have 2Cl, we multiply 0.05 times 2, it is 0.10 molar in Cl, and this is 0.15 molar in particles. And ACl, 0.5 molar in A plus and 0.51 molar in NaCl. The total is 0.30 molar in particles. HCl, the same. Complete ionization, 0.20 molar in particles. Now, acetic acid, weak electrolyte, between 0.05 and 0.1 molar in particles. Now, 0.1 sucrose, non-electrolyte, you have only 0.1 molar in particles. So, as we said here, the lowest freezing point will correspond to the solution with the greatest concentration of solute particles. Which one is the greatest? This is the NaCl, so it comes number 1 here. Na, 0.15 molar NaCl, the lowest freezing point, and then we go from 0.3 to 0.1 molar HCl because it is 0.2, and then we go to 0.05 molar CaCl2 because it's 0.15, and then you go to sucrose because it is a complete 0.1, and then finally acetic acid because it's between 0.05 and 0.1, and this has the highest freezing point. So this is your arrangement. So an ACl, less than this, less than this, less than, etc. Now we come to the final topic in this chapter called osmosis. Some substances form semi-permeable membranes, allowing some smaller particles to pass through, but blocking one larger particles. Now in biological systems, most semi-permeable membranes allow water to pass through, but solutes are not free to do so. And it also block larger molecules or ions. Now this selectivity gives rise to some interesting and important applications. Consider a situation in which only solvent molecules are able to pass through a membrane. If such a membrane is placed between two solutions, different concentration solvent molecules move in both directions. Now the concentration of solvent is higher in solution containing less solute. However, so the rate at which solvent passes from the less concentrated, the whole lower solute concentration, to the more concentrated solution, higher solute concentration, is greater than the rate in opposite direction. Thus, there is net movement of solvent molecules from the less concentrated solution into the more concentrated one. So in this process called osmosis, the net movement is always toward the solution with the higher solute concentration. So if we look at this illustration for osmosis, in osmosis the net movement of solvent is always toward the solution with the higher solute concentration. So there is a net movement of solvent through the semi-permeable membrane, as you can see here, as if the solutions were driven to attain equal concentration. The difference in liquid level and thus pressure eventually causes the flow to cease. Applying pressure to the arm here with the higher liquid level can also stop the flow. So again here we have semi-permeable membrane. We have here dilute solution, concentrated solution. So here we have net movement of solvent from the pure solvent or a solution with low solute concentration to a solution with higher solute concentration. And then here osmosis stops when the column of a solution on the left here becomes high enough to exert sufficient pressure at the membrane to counter the net movement of the solvent. Now at this point here, the solution on the left has become more dilute, but there still exists a difference in concentration between the two solutions. However, here, applied pressure on the left arm of the apparatus stops net movement of solvent from the right side to the from the right side of the semi-permeable membrane to the. Now this applied pressure is the osmotic pressure of the solution. So what we conclude? We conclude that there is something called osmotic pressure, which is the pressure required to stop osmosis, known as osmotic pressure pi, and can be found or calculated by this law, pi equal mRT, where m is the molarity of the solution. Now, if the osmotic pressure is the same at both sides of a membrane, the solutions are isotonic. Now, let's see this sample exercise regarding calculation involving osmotic pressure. Directly, the average osmotic pressure of blood is 7.7 at the what molality of glucose will be isotonic with the blood. And then you can find the molarity directly. This is the osmotic pressure divided by R times T. Remember, T must be in Kelvin. And you have this 0.31 molar. This is the molality of glucose that is isotonic with blood. And actually half of it, 0.16 molar solution of NaCl is 0.9 mass per cent in NaCl. This kind of solution is known as a physiological saline solution. You can solve the practice exercise by yourself. Then we come to the last thing, determination of molar mass. The colligative properties of solutions provide a useful means of determining molar mass. Any of the four colligative properties can be used, as shown in the following sample exercises. Now, the first one, molar mass for boiling point elevation. A solution of an unknown non-volatile non-electrolyte was prepared by dissolving 0.250 gram of substance in 40 gram of CCl4. The boiling point of the resultant is this, higher than that of the pure. Calculate the molar mass of the solute. So our goal is to calculate the molar mass of a solute based on knowledge of the boiling point elevation of its solution, and as delta Tb is given, and the masses of solute and solvent. From the table, we get Kb for CCl4, this value. Now, we can use the equation delta Tb equal Kb to calculate the molality of the solution. Then, molality equal delta Tb, which is this, divided by Kb for CCl4, and we get this molality. Now, the solution contains this amount mole of solute per kilogram of solvent. The solution was prepared using 40 gram, 0.04 kilogram of solvent. The number of moles of solute in the solution is therefore this kilogram times the molality, moles per kilogram, and this is the number of moles of solute. Now, the molar mass of the solute is the number of grams per mole of the substance. Molar mass equal mass over number of moles. It's 88 gram per mole. So this is the molar mass of the solute. Now, the second application, molar mass from osmotic pressure. The osmotic pressure of an aqueous solution of a certain protein was measured to determine the protein's molar mass. The solution contained 3.50 mg of protein dissolved in sufficient water to form 5 ml of solution. The osmotic pressure of the solution at 25 degrees centigrade was found to be 1.54 torr. Treating the protein as a non-electrolyte, calculate the molar mass. So here, first of all, we find molarity. The osmotic pressure is given. We convert it to atmosphere. R, T are given. We determine is the molarity. Molarity, moles per liter. We determine the molarity. And because the volume of the solution is 5 ml, we convert it to liter. The number of moles of protein must be moles equal this times moles per liter. The molarity here, moles per liter, molarity times volume, and we have this is the number of moles. Then after that, The molar mass is the number of grams per mole of substance. The sample has a mass of 3.50 milligram, and we convert it to gram. So the molar mass is the number of grams divided by the number of moles. إذن molar mass grams mass على molar mass, and we get this is the molar mass of our proteins. Because small pressures can be measured easily and accurately, osmotic pressure measurements provide a useful way to determine the molar masses of large molecules, such as proteins. Also, here you can practice by solving the following practice exercise. Thank you. End of part 2.